video, we looked at future value calculations with annuities. Now we're going to look at present value calculations with annuities. Here's a typical example of a problem. Herbert decides to give some money to his school to start the Herbert Scholarship in Mathematics. He wants to provide enough money so that a single scholarship of $2,000 can be awarded at the end of each year for the next 20 years. So there will be 20 withdrawals from the account that he sets up, each of which will be $2,000. The school tells him that his investment, which he gives them now as a lump sum, is going to be placed in an account that guarantees 3% per annum interest, compounded annually, from which the $2,000 will be withdrawn each year. So he will give them money, they will invest that in an account, and draw off $2,000 each year for the next 20 years, so that at the end of 20 years, all the money is exhausted and the balance in that account is zero. The question is, how much does he need to give now so that the funds last for 20 years? And assume the first scholarship is awarded 1 year from now. So that's a fairly complicated situation. Let's set it up with a timeline like we did in the previous lesson, where compounding periods go across the top and payment goes along the bottom. So if it's going to be for 20 years and the compounding period is 1 year long, there will be 20 compounding periods. So we can set the top up like this. And he's going to be placing a lump sum payment into the account now, so that's a lump sum into the account. But then there's going to be $2,000 withdrawals from the account at the end of each year starting 1 year from now. So we can place $2,000 here yearly. Now in order to keep these $2,000 distinct from each other, I'm going to number them. So this is the first 2,000, this is the second 2,000, this is the third 2,000, etc. So that doesn't change the value, it's just a way of us keeping them straight. Now let's deal with these lump sums one at a time. First, considering the first one, if I want to know how much money I need to put in now to withdraw $2,000 1 year from now, let's think back to our compound interest lesson. If I want $2,000 1 year from now, the calculation that I would do is this one. Because I'm earning 3% interest per year, so whatever principal or present value I put in now is going to be multiplied by 1.03 over the course of the next year-long compounding period. And if I want that to equal $2,000, this is the equation I set up. If I want to solve for this unknown present value, this unknown principal, to know how much I need to put in now to have $2,000 a year from now at an interest rate of 3%, so this number is 1.03, I solve for present value by dividing both sides by 1.03. That means this is the amount of money I need to put in right now to have $2,000 interest if the account pays 3% per annum interest. So this $2,000 right now has a present value of 2,000 divided by 1.03. Now let's consider the next 2,000. For that 2,000, which is the second 2,000, this one was the first one, I need to invest some amount of money, the present value, but it's going to be in the account, or the amount that I need to put in now for this $2,000 in the future is going to be in the account for 2 compounding periods. And each compounding period, it's getting multiplied by 1.03. Again, the amount of money I put in now, if I think of it as being marked for this $2,000, it's going to get multiplied by 1.03 in the first compounding period and 1.03 in the second compounding period, or multiplied by 1.03 squared. So this calculation is the one I would do to work out the present value of $2,000 in this account 2 compounding periods from now. Solving for the present value, I get 2,000 divided by 1.03 squared. So that's the present value of the second $2,000. In other words, it's the amount of money I need to put in now to have $2,000 in 2 compounding periods in this account. The third one, following the pattern, would be 2,000 divided by 1.03 cubed. And if I follow along, you can see that this 2,000 would have a present value of 2,000 divided by 1.03 to the power of 20. The subscripts match the exponents. That means that to have $2,000 20 years from now, I would need to invest this amount of money now in an account paying 3% per annum interest compounded annually. Now let's notice 2 things. First of all, as we go down in the column, each time we are multiplying by 1.03 in the denominator. In other words, this is a geometric series where at each step we're multiplying by 1 over 1.03 to get the next term in the series. Also, notice that This column is the present value of each individual payment. So if we sum this column, we get the total present value of all these payments stretched out over time. In other words, we get the lump sum that needs to be invested in this account now. So the sum of this geometric series, which has a common ratio of 1 over 1.03, is the value that we're looking for, the lump sum that needs to be put into the account now. So this is a geometric series, and its first term is the topmost term in that column, which is 2,000 divided by 1.03. We said that the common ratio is 1 over 1.03. There are 20 terms in that series, and we know that the formula for the sum of a series is a, the first term, times r to the power of n minus 1 all over r minus 1. If we plug those values above into the formula, we get 2,000 over 1.03 times 1 over 1.03 to the power of 20 minus 1 all over 1 divided by 1.03 minus 1. And if you put that into your calculator and carefully evaluate it, making sure that you put brackets in the right places, etc., then you get a value of about $29,754.95. That's how much money would need to be put into the account now so that $2,000 could be drawn off every year for the next 20 years and have a balance of 0 at the end. Now, using the formula for the sum of a geometric series, we can show that the present value of an annuity is given by this formula. PV, present value, is equal to R, the regular payment, times 1 minus brackets 1 plus I, the interest rate per compounding period, expressed as a decimal, close brackets to the power of negative n, where n is the number of compounding periods, all divided by I. So let's take a look at an example which we'll solve using the formula. Herbert takes out a $300,000 mortgage to buy a house. The mortgage agreement states that he'll pay equal monthly payments of $2,000 until the balance is paid off. If the bank is charging him 6% per annum interest compounded monthly, how long would it take him to pay off the loan under these terms? So here's the formula that we just looked at. And we know that the present value is given to us in the question as $300,000. The regular payment that he's going to be making is $2,000. The interest rate per compounding period is 0.06 divided by 12, which we can simplify to 0.005. And n, the number of compounding periods, is what we don't know and what we're looking for in the question. So if we plug in those numbers, we get 300,000 is equal to 2,000 times 1 minus 1.005 to the power of negative n all over 0.005. Dividing both sides by 2,000 and multiplying both sides by 0.005, we get 0.75 is equal to 1 minus 1.005 to the power of negative n. Rearranging this a little bit, we get 1.005 to the power of negative n is equal to 0.25. And now we want to get the n out of the exponent. Now you could do this by guess and check or using a table on your calculator or by finding the intersection between y is equal to 0.25 and y is equal to 1.005 to the power of negative n. I'm going to use logarithms. So if I take the base 10 logarithm of both sides, I get log of 1.005 to the power of negative n is equal to log of 0.25. Bringing the negative n down, I get negative n log 1.005 is equal to the log of 0.25. And dividing both sides by negative log of 1.005, I get n is equal to negative log of 0.25 divided by the log of 1.005. And if I put that into my calculator, I get approximately 278, or because n was in months, we're talking about a month-long compounding period, approximately 278 months, which is equal to 23 years and 2 months. So that's how long it would take him to pay that off, given the terms of the mortgage. Now, to solve that question on a TI-83 or TI-84 calculator, we would go to Apps, choose Finance, and then choose TVM Solver. Then we get a screen that looks like this. N is the number of compounding periods. That's what we don't know, so we're going to leave that blank for now. I% is the interest rate per compounding period as a percent, so that's going to be 6% divided by 12 because there are 12 months in a year. Present value is how much money he's being given from the mortgage now. He's getting $300,000 in his pocket, so it's positive from the bank now to buy the house, so that is positive $300,000. Payment is going to be negative though, because he is paying out of his pocket back to the bank $2,000 every month. And the future value is going to be 0 because at the end of all of this, we want him to pay the bank back in full, including all the principal and all the interest. We're going to leave these at the bottom here as they are, as we said in the previous video, because we've taken care of all the adjustments for the length of the compounding period up here. So we're going to leave this as 1, 1, and end because payments happen at the end of each compounding period. So now we come back up to n, and we press alpha solve, and we get 277.95, etc., meaning that approximately 278 compounding periods need to pass for him to pay off the loan entirely. And we said that that's 278 months, or approximately 23 years and 2 months. So that's an introduction to annuities and present value calculations.